when hard water is used for boiler, it leads to so many problems. The first problem we have discussed, that is scale and sludge formation. The second one is priming and foaming. So when boiler water is boiling with very high rate, that is on vigorous boiling, some liquid droplets carried along with the stream. So this is not happening in ordinary cases or in low pressure boiler. When high pressure water boils vigorously, steam carries liquid droplets. So once only steam alone goes, it cannot carry any salts, it cannot carry any dissolved gases. Since steam goes with some droplets of water, it carries some dissolved solids, suspended impurities, and so on. So here that steam goes with some liquid droplets, and that liquid droplets are carrying some of the dissolved salts and suspended impurities. So this is called as carryover. It is very simple. When water is boiling vigorously in a boiler, liquid droplets goes with the steam, and liquid droplets are going with some dissolved salts and suspended impurities. It is called as carryover. So this carryover occurs because of two means. One is priming, another one is foaming. There's a slight difference between these two. So priming is process of production of wet steam. That process is called as a process of production of wet steam is called as priming, whereas foaming, see that term foam, formation of stable bubbles. So when water boils on the surface, you can see the bubbles. So normally when oil boils, there will be some bubble on the surface. Similarly, formation of stable bubbles on the surface of water. Since we are getting such bubbles, it is enhancing the rate of priming. So this bubbles tends to go with the steam, that is priming is enhanced. Now let us concentrate on this priming. So priming, I specified earlier, process of production of wet steam. It is caused by high steam viscosity. I specified earlier, this is not happening in low pressure boil. In high pressure boil, when steam goes with very high viscosity and water level in the boiler is high, when once water level in the boiler is high, that is that exit of the steam is close to the water level, then there is a chance of going liquid droplets with the steam and sudden boiling. So when water boils suddenly, there may be some bumping may take place, and which leads to priming. And sometimes the design of the boiler itself may not be that much perfect, and it may carry some liquid droplets, which leads to priming. So how to prevent it? These things. So these are the reasons responsible for priming. Once these things are avoided, naturally the boiler is going to be a better one, which is not going to give any priming. So control the viscosity, keep lower water level to the required level, and have better boiler design, and use treated water. So like this priming can be. When we coming to foaming, foaming is nothing but formation of stable bubbles on the surface of water, and these bubbles will go with the steam as liquid droplets, and which will carry some dissolved solids, right? And how this is caused? it is caused mainly due to oil. In case if there is some oil or grease or some hydrocarbon present in water, which tends to form bubbles. So the water which we are using should be free from oil, grease, so that we can avoid foaming. Or we can add some coagulants. It can be prevented by adding some coagulants like sodium aluminate is a very good, very better coagulant, so which will coagulate that oils and grease so that there won't be any foaming. Or some anti-foaming agents itself we can anti-foaming, which will prevent the foaming rate. So anti-foaming agent like polyamide we can add to prevent this foaming. So this is the second boiler bead water defect. The third one is Kazakh embrittlement. So this Kazakh embrittlement is nothing but intercrystalline cracking of boiler metal. It is more dangerous when compared with other defects. See, the cracking of boiler metal, boiler itself is getting cracked. So how it causes? Normally we cannot get always soft water. So the hard water which we have is treated by so many methods. One such method is our lime soda process. To get soft water we are using lime soda process. In lime soda process we are using sodium carbonate. So the sodium carbonate which is used in lime soda process may present with the boiler feed water. See, that sodium carbonate we added during lime soda process, which remains with the boiler feed water. So when water boils in boiler, that sodium carbonate traces present in boiler feed water decomposes to give sodium hydroxide. So now there is no sodium carbonate in that boiler, we have sodium hydroxide. So when water boils, concentration of sodium hydroxide increases, and that concentrated sodium hydroxide goes into the hair cracks of boiler metal. So it goes into the minute hair cracks of the boiler metal and reacting with iron and forming soluble sodium ferroate. So it goes into the crack, reacting with iron, forming soluble sodium ferroate. It is soluble, that means whenever, if it is not forming any soluble compound, okay, but it is forming soluble, that means it is breaking the boiler metal. And normally this boiler metal breaking occurs mainly in the stressed parts of the boiler, that is bends and joints where we have more stress. So there is the metal is weakened, so there the embrittlement taking place at a faster rate. So very simple, sodium carbonate which you added during lime soda process undergoes decomposition giving you sodium hydroxide. When water boils, concentration of sodium hydroxide increases, it goes into the minute hair cracks of the boiler metal, reacting with it, forming soluble, that is water soluble iron compound, that is sodium ferroate. Since the metal is removed, that is there is a breaking, it is happening mainly in the stressed parts like bends and joints. So how it can be prevented? So very simple. Since you are having sodium carbonate, there is embrittlement, there is caustic embrittlement. In case there is no sodium carbonate, there will not be any such. So keeping that in mind, instead of sodium carbonate, we are adding sodium phosphate during lime soda process. That is one thing. And another thing, only when there is some minute hair crack, the sodium hydroxide, if any formed, can goes into that. So avoid that hair cracks, but that may not be possible. So what we are doing is we are adding some compounds, tannin, lignin, which blocks the hair cracks. So even if any sodium hydroxide formed by the decomposition of sodium carbonate, there won't be any such embrittlement of the boiler metal, so we can avoid. When you are using hot water as a boiler feed water, we are getting so many problems. So we have so far discussed 3 problems. The 4th one is boiler corrosion. So when you are using hot water as a boiler feed water, the boiler may get corroded. So what are the reasons or the responsible constituents causing corrosion to boiler? One is DO, dissolved oxygen, and dissolved carbon dioxide. These 2 dissolved gases. Besides, dissolved solids are responsible for boiler corrosion. First, let us see how this dissolved oxygen is responsible for boiler corrosion. So corrosion is an oxidation process. If there is oxygen and if there is moisture, metals will readily react to form the respective compounds. So here the boiler is made up of iron react with oxygen in presence of water, forming iron hydroxide, that is, boiler is getting corroded. So how to avoid this boiler corrosion occurring in presence of oxygen? So very simple thing, since you are having dissolved oxygen, there is boiler corrosion. Once we remove the dissolved oxygen, then there won't be any boiler corrosion due to dissolved oxygen. So we have 2 methods for the removal of dissolved oxygen. One is chemical treatment and another one is mechanical deaeration. These 2 methods are used to remove dissolved oxygen. So in chemical treatment, the boiler feed water is treated with sodium sulfite, which is readily traps oxygen, forming sodium sulfate. So the oxygen, dissolved oxygen, is completely removed. And hydrogen, which is also combining with oxygen, forming nitrogen and water. So if there is any dissolved oxygen, on adding sodium sulfite, Na2SO3, sodium sulfite, or by adding hydrogen, the oxygen, dissolved oxygen, is trapped and converted into sodium sulfate and nitrogen and water respectively. So when you are comparing these 2, which one is superior, sodium sulfite or hydrogen, which is superior? Here we are adding sodium sulfite into boiler feed water, which is forming sodium sulfate, which is another chemical, whereas in the case of hydrogen, we are getting nitrogen, an inert gas, and water, which is no way going to affect the composition. Since we are getting such inert nitrogen and water, this is superior over our sodium sulfite. So preferably we are using hydrogen than sodium sulfite. Now the second method for the removal of oxygen is mechanical deaeration. And for that we have this setup, mechanical deaeration setup. So this is a tank, a tower, having raw water feed at the top and deaerated water we are getting at the bottom. And this tower is heated with heater on either side. On either side it is heated, and inside the tower we have perforated plates. It's only a cross section, so we have perforated plates, and here this is attached with vacuum pump. That means pressure inside the tower is decreased For that it is attached to vacuum pump. So we are feeding the water which is having oxygen, dissolved oxygen. From the top it is sprayed, and we have perforations as I specified earlier. When this is heated, using this heater it is heated, simultaneously the pressure is reduced. Inside the pressure it is reduced because we have attached the vacuum pump, pressure is decreased. So at high temperature and low pressure, the dissolved oxygen is removed by the vacuum pump, and water we are getting is free from oxygen. So very easily, without adding any chemical, we are achieving deaeration. This is the second method. So these are the two methods by which we can remove DO to avoid boiler corrosion due to dissolved oxygen. So the second component responsible for boiler corrosion is carbon dioxide, dissolved carbon dioxide. All we know, carbon dioxide is acidic. Carbon dioxide present in water, reacting with water, dissolving with water, forming H2CO3, carbonic acid. Of course, it's a weak acid forming carbonic acid. CO2 reacts with water forming carbonic acid. It is acidic. Any acidic substance present in water on contact with metal leads to corrosion, all we know. So this H2CO3 is responsible for corrosion. The next to dissolved oxygen, the other component, other dissolved gas responsible for boiler corrosion is dissolved carbon dioxide. All we know, carbon dioxide is acidic. So that carbon dioxide reacting with water forming carbonic acid. Any acid on contact with the metal leads to corrosion. So carbonic acid is also responsible for that. And this carbon dioxide, which is present in dissolved form, that is one thing. And carbon dioxide is produced by the other source, that is calcium bicarbonate, which is present in hot water. So when hot water is used as a boiler feed water, when water boils, calcium bicarbonate decomposes to give calcium carbonate with the formation of carbon dioxide. So this corrosion due to dissolved carbon dioxide is not only due to the dissolved CO2 which is already present, which is also produced due to the decomposition of calcium bicarbonate giving carbon dioxide. So if carbon dioxide allowed to remain in water, in boiler feed water, that is going to give corrosion. So it has to be removed. We have two methods to remove. Since it is an acidic oxide, it can be removed by adding a basic substance like ammonium hydroxide. So ammonium hydroxide base, carbon dioxide acidic, forming ammonium carbonate. So calculated quantity of ammonium hydroxide is added into the boiler feed water to remove carbon dioxide as ammonium carbonate. Ammonium carbonate being neutral, it is not going to give any corrosion. And CO2 can be removed by deaeration as we have done earlier. So here we have deaerated water. Simultaneously CO2 can also be removed by the same mechanical deaeration method. That means by this mechanical deaeration method we can remove all the dissolved gases, especially carbon dioxide and oxygen. So the third component responsible for boiler corrosion is dissolved salt. Our hot water may contain the salts like magnesium chloride and calcium chloride. Normally a salt will undergo hydrolysis. By hydrolysis they will give acid and base. All we know, acid reacts with the base forming salt and water. So when salt undergoes hydrolysis, giving back an acid and base. As we know, whenever some acid is present in water, when it contacts with the boiler metal, leads to corrosion. So the acid formation has to be prevented, or the acid form has to be removed. Then only the corrosion can be avoided. So here I have taken magnesium chloride as an example. It undergoes hydrolysis, giving you magnesium chloride undergoes hydrolysis to give magnesium hydroxide plus hydrochloric acid. Acid is produced. And this acid produced here is corroding boiler metal. See, boiler is made up of steel. So ion react with HCl produced here. HCl produced by the hydrolysis of magnesium chloride, which is reacting with boiler feed metal, forming ferrous chloride. With the removed chloride undergoes hydrolysis to give hydrochloric acid. That hydrochloric acid reacting with the metal of the boiler, forming FeCl2 with the removal of hydrogen. So FeCl2 getting dissolved in water, forming FeOH twice with the production of again hydrochloric acid. So this HCl again will react with iron. So that process goes. That means once this process initiated, the hydrochloric acid or any acid produced is not consumed, it is regenerated. So once corrosion started, it is going to be a continuous process. So his acid produced has to be removed. So how it is removed? So corrosion by acid can be avoided by adding alkali. So we are going to remove acid, so we can add some alkali, that is sodium hydroxide we are adding to remove the acid formed as salt and water. So once we are adding calculated quantity of sodium hydroxide, here we cannot add any ammonium hydroxide because it is a weak base. We need strong base like sodium hydroxide to remove the acid, either HCl or sulfuric acid formed. So HCl formed in this case is removed as sodium chloride on adding sodium hydroxide. So the corrosion due to dissolved solids can be avoided by removing the formed acid by adding sodium hydroxide.